Hello everyone. This lecture we will study further the integral or certain special types of functions by using the residue theorem. So the title will be Integral of Rational Functions. Recall that rational functions means it's a quotient of two polynomials, sine and cosine functions over intervals of length 2 pi. The title is long, but the formula is easy. We will consider the following integral r cosine theta sine theta dz, where r is pxy divided by qxy. Okay, is a rational function. And of course, it's not globally defined for all x and y, but we assume that r cosine theta sine theta is well defined for theta in the interval from 0 to 2 pi. Okay, so for this type of functions, we will use the following U-Substitution. Recall that before when we have some complex variable z, we use z equals r times er theta to do the parametrization. Now we reverse the order. So before we set z equals r ei theta to calculate now we replace cosine sine by functions of z. So that's a key idea. Because we want to use the residue theorem, you need to have holomorphic functions instead of just real functions. Here, cosine itself is a real function. Okay. Just a small remark. Why not take theta to be a complex variable? Then if you did that, for example, then you have omega sine omega. This is a holomorphic function, but the problem is holomorphic. But in general, it is hard to control the arrow turns in a residue theory. That's a drawback. I'm not saying you cannot do it definitely, but you will see in a lot of cases this is not ideal. Okay, so the method is z equals ei theta, then cosine theta is z plus 1 over z. Recall 1 over z is exponential negative I theta. Divided by 2, sine theta is z minus 1 over z divided by 2i. And d theta is dz divided by iz. Okay, then the line integral of r cosine sine d theta is let me keep it, is line integral of the function r z plus 1 over z divided by 2, z minus 1 over z divided by 2i dz iz. And here the orientation is counterclockwise. And noted that if we write it in this way, by the assumption r is rational, so this is a rational function. Of course, it's holomorphic, and on I should say holomorphic except certain points outside, not on the circle. And you might have, so if you draw a picture, so to calculate this, we can use the Residual Theorem. So it's 2 pi I summation residue A of f. So here f is defined to be the green box. Let's repeat it. Z minus 1 over z divided by 2i divided by iz. But here you need to make sure that you only collect the residue inside the circle. If you draw a picture, your circle is here, so you want to calculate the contour integral along the circle with the orientation counterclockwise, and then by the theorem you need to calculate the residue inside the circle. Of course, you might have, so let's call those A. You might have poles outside the circle, B, B1, B2, BK. Okay, so that's a general formula. You first do some U-substitution, transform the theta integral to z integral. Then you calculate the residue. We will do some exercise to get familiar with this method. So suppose now you have an integral from 0 to 2 pi d theta 1 minus 2a cosine theta plus a squared, where a is between 0 and 1. Okay, now let's see. So the solution. At the very beginning, we can do it step by step, write down all the details. If you get familiar with this method, you can speed up by skipping several intermediate steps. Cosine Oh, here you don't have sign, so it's not necessary to write the sign part. d theta is dz divided by iz. Okay, then the line integral equals 1 dz over iz, and the integral is 1 over 1 minus 2a times z plus 1 over z divided by 2 plus a squared. It's integral over z of the unit circle dz times 1 over dz over I. You times z to the second denominator and get 1 plus a squared z. So here you have a squared. You combine 1 plus a squared minus, so 2 cancel out with 2 here, and minus a z squared minus a. Okay, we simplify a little bit by flipping I to the numerator. So you have I dz az squared minus 1 plus a squared z plus 1. So your integrand is a holomorphic function I over az squared minus 1 plus a squared z plus 1. So next, try to locate the poles of this holomorphic function, that is the zeros or the denominator. Recall that the denominator can be factorized as az minus 1 times z minus a. Therefore, you have two poles. One is inside the unit disk is A. The other one is 1 over A outside the disk in this way. Recall that A and 1 over A not in the same line with the origin. They have the opposite angle. It's just from the complex multiplication. Okay, next we can apply the residue theorem. So apply residue theorem. So I equals, so I is just this one, 2 pi I times residue. Inside you only have one pole, so residue at A of the function I az squared minus 1 plus a squared z plus 1. Okay, since since all the function I over az squared minus 1 plus a squared z plus 1 has a simple pole at at A, then recall previous how to calculate the residue. We can transform the residue to derivative. So this is the limit, zero's derivative, or just a limit, since you have simple pole. If you have high order poles, then you need to take a derivative. We will give you another example later. Z minus a z squared minus 1 plus a squared z plus a. So if you forget the formula here, go back to lecture 11 to find 11 or 12 to find the formula therein, how to calculate the residue. Okay, then you can just cancel out z minus a with z minus a in the denominator. Okay, then take the limit. You have 1 over a squared minus 1. If you plug in, then I is minus 2 pi times 1 over a squared minus a. Minus 1 is 2 pi 1 minus a squared. Okay, so let's make a remark. First remark is when we do calculation, we may make mistakes on the side. So it is convenient to avoid this type of mistakes by checking the sign of the original function or original integral. For example, here at the very beginning, you see the integrand is positive. Therefore, I should be positive no matter what value it is. So if at the end you have, for example, 2 pi over a squared minus 1, then you must make mistake. Okay, and the second remark, it's a natural question why we restrict this to this type of thing. So, for example, if we let a be a positive number greater than 1, if a, what is I, capital I? So everything is the same except when you compute the residue here. Now when you locate the poles, here you have A outside the disk and 1 over A inside the disk. Therefore, you need to multiply, so residue 1 over a z squared minus 1 plus a squared z plus 1 is limit z goes to 1 over a z minus 1 over a z minus 1 z times I, z minus a. So this is limit z goes to 1 over a I over a times z minus a. So this is I times a times 1 over a minus a is I 1 minus a squared. And then you plug into the residue theorem. You have 2 2 pi a squared minus 1 when a greater than 1. Okay, and then a small question is, what if the critical point, if a is 0, then it's trivial, and negative, then you only need to translate theta by pi over 2 or pi, so they're same. So what if a less than 0, and probably a little bit difficult one is, what if a is 1? I don't have definite answer right now, but then you can see if you plug it into the formula, either this one or this one, you will see the integral goes to infinity. Okay, so that's a residual theorem for this type of special functions. Next, we discuss the integral of rational functions over the real line with degree of the denominator at least 2 more than that of numerator. In other words, we want to consider the integral for x from negative infinity to positive infinity of the function px divided by qx. P, q are polynomials, and under the condition degree qx greater than or equal to degree px plus 2. And of course, for this moment, we assume the denominator is different from 0 when x is a real number. Okay, and the solution from previous experience, when you have a real number line as your domain to integrate, then naturally you will construct a long line along the x-axis combined with an up hemicircle. And if you make the radius greater and greater, then eventually one side you get the original real integral. The other side you have the up hemicircle and the residue part. Residue part comes from the poles of the rational function, so probably you have certain poles inside Z1, Z2, Zn. Okay. So if you summarize this in words, then compute the integrals of P over Q over the contour of the boundary up half disk or radius R centered at the origin as R goes to infinity. So that's a general procedure, but to get the conclusion, we still need to work a little bit, but then the result is very clean. You don't have the continuous part. To be more precise, the original integral equals 2 pi I times the summation of residues whose imaginary part is positive. Okay, a small remark is the choice of the up hemisphere has no advantage over the lower hemisphere. Actually, you also had the following formula. You just take one of sides. Later on, when we have exponential iz, or sine, cosine, then we have differences between positive up half plane and the negative lower half plane. Lower half plane. Okay. Because of the decay of exponential iz only along the positive direction. So before we prove this, let's look at what does this mean. This means that intuitively, this means you can throw away the circular boundary. Okay, to be more precise, we need to set up everything and do estimate. So let gamma r be the contour of negative r to r union the curve REI theta, where theta is between 0 to pi. 0 to pi. Okay. And with the usual orientation, or the counterclockwise orientation. Now write QZ equals AZM to the mth power times 1 plus A1 over Z plus A2 over Z squared plus all the way to AM over Z to the mth power, and the PZ is BZ to nth power 1 plus B1Z plus B2Z squared plus BNZ to N, where A, B different from 0, and by assumption M is greater than M plus 2. And what we are doing actually, if you use some fancy language, is the Taylor expansion at Z equals infinity. Later on, if we learn a Riemann surface or Riemann sphere, we know infinity is covered by another complex plane, and through the transition function Z equals 1 over omega. Okay, now let's estimate the circular part PZ over QZ dZ. Of course, you need to so first let's plug in the previous formulas: z to m's power, bz to n's power times 1 plus a1 over z plus a2 over z squared plus all the way to am over z to m's power divided by 1 plus b1z plus b2z squared plus bn to z to n's power. Okay, then let's parameterize it. So the parameterization is z equals rei theta. So the integral is from 0 to pi because of the orientation. And then inside you have b over a times oh, sorry, my bad. Here actually b is upstairs, a is downstairs. My bad. A1, A2, AM. Okay, then you have exponential I m minus m theta and times, okay, you have dz, d theta, dz is rei theta times I and divided by r2 m minus n's power times exponential negative I theta r plus bn exponential negative I n theta divided by r2 n's power. Similarly for the numerator, for the denominator, you also have powers in m in the denominator. Okay, and then you simplify, you noted that you can factor out 1 over r to the m minus m minus 1's power times b times over a, and then inside, no matter what, you do have some formula. D theta, and then we need to bound the integral, but then noted that the green part is bounded when r larger enough. So when r larger enough, for example, you can choose r larger than greater than the maximum or a1 am norm, b1 bn norm, then for instance, then the green box, the absolute value of the green part is less than or equal to, you take absolute value of the exponential I n minus m plus 1 theta, it's 1. And then for the numerator, you have Okay, I see. Okay, so for this is not enough. You need to times m plus, for example, 100. Okay, for the numerator, you can just enlarge it and bound it by n, because you n plus 1, because you have n plus 1 terms. And then for the numerator, you greater than 1 minus a1 norm divided by r minus a2 norm divided by r minus a m norm divided by r, and then by the assumption 2m plus 100. So this will be less than theta from 0 to pi m plus 1 divided by 1 minus 1 over 2m times m d theta, which is bounded by 2 pi times m plus 1. But it depends on m, but the advantage is it's independent of r. That's enough. So the bound is independent of r. Of course, here you need to assume when r greater than this. Okay, then if you take the limit when r goes to positive infinity, dz. So green part is bounded, but now by the assumption m minus n minus 1 is greater than or equal to 1. B and A are different from 0. So the limit is 0. Okay, then now consider the horizontal line integral. So we can conclude the integral for x from negative r to r, px over qx dx, is minus the circular line integral plus 2 pi I times summation residue A. And because of the shape of the contour, here for the residue part, we only consider those poles where the norm is less than r and the imaginary part is positive, pz, qz. Okay, let r goes to positive infinity. The left hand side is a real integral we want, and right hand side, this goes to 0, and then this part, because r goes to infinity, then when you do the summation, you do have to include all the poles whose imaginary part is positive. There's no restriction on the magnitude of the poles. Okay, and as we remarked before, exactly the same way we can conclude that the real integral is 2 pi I. Imagine a less than 0 restriction or residue of the rational function at point A. Because here, no matter you choose the up half plane or up half circle or the lower half circle, you have factor 1 over r out of the integral. If you choose the lower half circle, you also have the factor 1 over r. Then when you take r goes to infinity, that just control your arrow and force your arrow to be 0. Okay, next let's look at an example. The x squared plus 1 cubed equals 2 pi. So by the previous formula, we need to calculate. Oh, of course, first you need to verify the assumptions. And the degree of the denominator is 6, and the degree of the numerator is 0. And moreover, the poles are negative I and I, so it's not on the real number line. Okay, then by the previous theorem is 2 pi I summation imaginary part residue at the poles with positive imaginary part. So here is residue at I 1 over z squared plus 1 cube. And then here, notice that it's not simple pole. So when you apply the derivative method to calculate the residue, we need to do the following: 1 over 2 factorial second derivative of z minus I cube z squared plus 1 cube evaluated at z equals I. And then it's times 1/2 times second derivative of 1 over z plus I cube evaluated at the pole, and it's pi I times -3, -4 z plus I to 5th power z equals I, and then it's pi I times 12 times 2i fifths, 1 over 2i to the 5th. So it's 12 pi divided by 32, which is 3 pi over 8. Okay, and now let's verify the remark, which says we can also calculate the residues in the half plane. So I, let's denote this as I, equals 2 pi I residue z equals negative I 1 over z squared plus 1 cube, and 2 pi I still similarly 1 over 2 factorial second derivative z plus I cube z squared plus 1 cube z equals negative I. And then you plug in, you have 2 pi I times 1/2 times second derivative of 1 over z minus I cube, and then 2 pi I times 1/2 minus 3 minus 4 1/z minus I to the fifth, z equals negative I. So this is 2 pi I times 6 times negative 2I to the fifth 1. So what's the answer? Negative I. Oh shoot. Yeah, you have negative sign here, kind of. So let's see what's the problem here. Z plus I. Yeah, I will get back to you next time. So, but you can also think about what's the problem here. You expect the same answer, but here seems like you have a negative sign. Okay, next we will study. I will get back to you next time. So integral of product of sine, cosine function and rational functions with real coefficient over real number line with degree of the denominator at least 1 more than that of the numerator. So if you write down, it's pretty similar to the previous case, but then here you might twist it with cosine and sine. Cosine or sine. And the assumption on P and Q is that their coefficients are real. But the assumption degree of Q at least 2 over 2 plus the degree of P is relaxed to 1 more than the degree of P, degree of Qx, Px plus 1, and no zero of Qx for real x except simple ones at zeros of sine or cosine or sine respectively. So here you actually have very subtle places. Let's explain one by one. So firstly, so why real coefficients? So the reason is because we want to realize Px, Qx, cosine x as a real part of Pz, Qz, exponential Iz, or if you like, real part of P over Q times exponential negative Iz. if P and Q have coefficient not real, then when you take a real part, you have different value. It holds if P and Q have real coefficients. So the idea is you have real integral involving cosine or sine, then you complexify it to get some holomorphic function. And then how do you go from holomorphic function to the original integral? So here, because we want to twist it by exponential iz, then the way go back is to take the real part or imaginary part. So similarly, px over qx sine x is the imaginary part of p z q z exponential I z, or negative imaginary part p z q z exponential negative I z. Okay, so this is first thing, why real. Secondly, what is the contour? So according to the function, holomorphic function p over q exponential I z, then we would like to consider the boundary of the upper disk in go this way, and then let r goes to infinity. And if you choose p over q times exponential negative I z, then the suitable contour will be on the lower half plane. So why? Consider because of the decay of exponential I z. Actually, the decay is subtle here. We haven't talked about the degree assumption, but at least you know if you consider the contour in the lower half plane, then exponential I z goes to infinity, because I times a negative I times y is exponential y. Here y is positive number. So let me see. If y is positive, then exponential negative iy is exponential y goes to infinity when y goes to infinity. Therefore, contour in the lower half plane loses control on exponential iz. Similarly, if y is we still let y to be positive, then exponential I iy. This is in the up half plane. It's exponential negative y. Oh, sorry, your function now is this one. It's positive y goes to infinity when y goes to infinity. Then contour in the up half plane loses the control of exponential negative iz. Okay, so the only possible way is for exponential iz, consider the contour on the upper half plane, and for the exponential negative iz, consider the contour in the lower half plane. But then more subtly, the degree assumption, if we bound exponential iz by 1 in the upper half plane, then you have some trouble. What is the trouble? The trouble is then pz, qz on the circular part, exponential iz, you bound it by pz over qz dz. Plug in the parametrization. Finally, you will have 1 over r times some function of theta and r. So this is the green part. It's bounded by a constant. And from the dz, you have actual r d theta. So here the fatal fact is r cancel out with r. This part is only bounded but not vanishes, but don't vanish. Sorry. But does not vanish when r goes to infinity. If you are not convinced by this, go back to the original proof when q, degree of q at least degree of p plus 2. Then you will see okay, next how to get over this, why 1 is enough. Then we, okay, so this means we cannot control arrow turns in such a naive way. A good part of exponential I theta is also it's a key point of the Fourier analysis is you have cancellation. You have cancellation. That means you need to use a special property of exponential I theta coupled with P over Q, not do estimate separately. So this is very subtle, and if you really think about it, it's related to the Riemann-Dirichlet lemma, that you shift the angle a little bit, then goes to 0. Yeah, I will not discuss this too much at this moment, but later on we will come back again. But here, a quick way to view this is quicker way. Next time we will give a more detailed discussion. Quick way. P over Q exponential IZ CR. You do integral by parts. Exponential IZ over I minus differential of P over Q times exponential IZ, still over the same loop, negative R to R. Okay, and then for the P over Q, this part, this is bounded because of the contour we choose. This is bounded by degree assumption. And then for the other part, after you take a derivative, you have P prime over Q, all minus Q squared PQ prime times exponential IZ CR. Now, the green box is degree of the denominator is 2 more than the degree of the numerator. So we can control this part easily. So this goes to 0. Okay, here I made a mistake. So vanishes actually. Not bounded. Vanishes. So this part also goes to 0 when R goes to partial infinity. So we realize the cancellation by integration by parts. Integration by parts actually is very important in mathematics. It's not, you can see it everywhere, even in PDE. Always the tricky part is integral by parts. But then the essential part is, I think in my point of view, is the cancellation. You need to have some good coupling. Exponential I zeta and P over Q. Exponential I zeta has good coupling. If you replace exponential I zeta by another rational function or holomorphic function, whatever it is, you take the derivative, you lose the control of the derivative. Because you don't know what is your derivative. But exponential I zeta, the derivative is still exponential I zeta. You have properties as good as before. Okay, I will stop here for this lecture. Next lecture we will give the exact formula for the integral of this type.